Your hook for today deals with the reading of this graph, this position versus time graph, and you're finding meaning in it. This is an indication of positions for Baby Mouse's busy day. And I would expect you to be able to mark with an S where Baby Mouse was taking a nap. And also to mark with an F where Baby Mouse was running from a cat. So please do that. And if in the course of the lecture you learn something and you want to change how you've marked this graph, feel free to go back and change your marks. Okay, we're going to start by talking about position. And the symbol I'll use for position is an X, sort of indicating where you are along an x-axis, a number line. We could also use a Y if we were talking about vertical position, or many other letters. Displacement, the symbol for displacement is delta x, and the delta means change. So we're talking about the change in position. That's what we mean by displacement. If I talked about how you had changed, then what I would be doing is comparing the way you are now with the way you used to be. And that comparison would be a matter of looking at the difference. And difference, of course, is subtraction. That whenever we refer to change, and we will refer to it a lot, we always mean this. And in this case, delta x means what is your position now? Subtract from that the position you had at the beginning. That's the change in position. So for example, if we started at -3 and we ended up at -2, then the final position is -2. The initial position was 3. I would subtract that 3 from -2. I get a -5. The change in position was 5 in the negative direction. We will learn that displacement is a vector quantity. That is, it not only has size, but it has direction. And when you are dealing with a vector quantity, as we continue today, would you please either put a positive or a negative in front? It doesn't need the plus sign to be positive, but it does indicate your conscious consideration of direction as well as magnitude. Contrasting with displacement is distance. And we will use a D for distance. Sometimes, more often next year in AP Physics, I will use an S for distance. And there's an S. What we mean is the total length of the path. And so you have this serpentine kind of path here. The total length of the path is what we mean by the distance. So, for example, here you have something starting again at 3 and ending at 6. And its displacement, well, that would be 6 minus 3. That would be positive 3. But the distance would be the total length of this path. Something closer to 9. Distance is not a vector. It does not have direction. We would say it is a scalar, but we'll talk more about vectors and scalars another time. Suppose we went again from 3 to -2, but in the middle we went to 5. Then the distance would be that how far it was from 3 to 5 plus how far it was to go from 5 to -2. And so the distance that you went in this case was 9. We don't really need the positive or negative because distance will always be a positive amount. It is how big it is. We don't have an issue of direction. What is missing from these and makes me want to itch is, so we really ought to put units. And you need to get careful with putting units on all of your answers. But we don't know the units here. These could be kilometers, they could be meters, they could be centimeters, all good. Okay, so we have position, we have displacement, we have a change in position, and then we can consider the rate at which you move through a distance. And that is called average speed. The rate at which you move through a distance. We contrast that with average velocity, which is the rate at which you displace. Notice this one would be a vector quantity. We want to be careful about the direction as well as the size. This one would be a scalar. Distinct and different definitions for speed and velocity, and you be careful that you know them. Know them all. Okay, so here are a couple of problems. There's a number line if you want its help in doing them, but I would like you to find the distance and displacement for this situation and the distance and displacement for this bit of motion. Please get units and direction where it's appropriate. Now, in contrast to average speed and average velocity, which we have already defined, notice here I've put units. Those would be the standard or fundamental units of speed and velocity. I also want to talk about instantaneous as opposed to average. Instantaneous velocity is tricky. That what I mean by the velocity at an instant is find the average velocity for a very, very short period of time containing the instant. I cannot measure instantaneous velocity directly because an instant has a delta t of 0, and that makes for an undefined fraction. What I have to do is approach it. And there is a limiting value that it approaches, and that is what we mean by the instantaneous velocity. The instantaneous speed, on the other hand, is not the same process of a limiting. The instantaneous speed is take the instantaneous velocity, which had both size and direction, and only consider its size. How fast was it going at that instant? That's what we mean by the instantaneous speed. Here are some problems for you to apply these ideas to, and we're not trying to do anything tricky here. You see what you can get as answers for those questions. Next, if I know the velocity of this man, and I know how far this man is away from the wall, then it is possible, without doing an experiment, for us to find out when he will reach the wall. Let's do the experiment anyway, though. So everybody get your stopwatches out, and on go, we will start timing, and we will see how long it takes for the man to get there. Ready, set, go. Oh, Mr. Houghton, you're so silly. But indeed, I need to make the point that when we said the velocity was 2, perhaps we said it was a positive 2, but we don't know what direction positive is. I had the man facing towards the wall, so you would assume that's the way the man was going to walk. But in fact, I had this number line. And in my number line, positive 2 meters per second was going backwards to the way the man is facing. And so we didn't know it. The man going at 2 meters per second, maybe the man was going up at 2 meters per second. Point. You need to be very careful what positive means, and it is perfectly valid for you to have a number line that has positive going upwards or positive going to the left. You just need to be conscious of what direction your number line goes and make sure your values, especially this one, are consistent with that signage. To repeat ourselves, there are these things called vectors, which have both size and direction. Contrasting with them are scalars, which do not have direction, they only have size. And just for the sake of trivia, there's also something which has neither size nor direction. This one doesn't have direction, but it still has size. But if you had neither size nor direction, that's called a coefficient. I give that to you for trivia. We will deal with some coefficients this year. It is not important that you learn that, however. Now, here is a graph of something's position at various times, and I would like to know what the velocity was from 1.5 to 2 seconds. That is, from 1.5 to 2 seconds. And I would like to know what the velocity was at 1.5 seconds. This one clearly instantaneous velocity, this one average velocity. And so what I'm going to do is to take the change in position divided by the change in time. Note that I decided that that was 8/10 of the way up there. 8/10 of 25 is 20, so 75 plus 20 is 95 is the initial, and the final was, I decided that was 3/10 of the way. 3/10 of 25 is 7.5 plus 50 makes 7.5. So I have that value. When I subtract them, this one is only known to the nearest whole number, so my arithmetic means this is only known to the nearest whole number. This one was only known to tenths, so the answer is only known to tenths. Properly, when I divide here, I should get this to 1 sig fig, and if indeed you said -8 times 10 meters per second, then that would be correct. But I really feel like I kind of know the displacements to 2 sig figs and the changes in time to 2 sig figs. I really feel good about this 0.76. It is an issue that we will wrestle with. Notice the negative, very important, that what you have really found is the slope of this line, and there's no question, but that's a negative slope. It has negative velocity. Now, as far as the velocity at 1.5, I would draw a tangent at 1.5. That is not an exact thing, drawing a tangent, and people will draw good tangents which differ slightly from this, and we're stuck with that. Unless this has a well-defined functional description, we cannot use calculus to get the instantaneous velocity, and we are stuck with drawing a tangent, finding its slope. Please do let me see the tangent that you draw. Oops, I got ahead of myself. As I said, we're finding the slope in a position versus time graph. Slope would be change in position over change in time, and that, of course, is what we mean by velocity. So that's what we're doing here. Again, I would take that at 3. I can take any 2 points along this line. I would take at 3, it's going through 100. No, it's going through 50, and at 1.5, I'll say it's going through 100, and then you do the arithmetic. Notice the difference between the average velocity and instantaneous velocity. We're not surprised. Suppose they asked you for the instantaneous speed here at 1.5. I hope you're aware that the answer would be 33 meters per second, the magnitude of the instantaneous velocity. So here are some points which are very important to me, and I will repeat several times. Instantaneous velocity really does exist, but you cannot measure it, because when you try to do delta t for an instant, you have a 0 there. So all measurements that we take will be average velocity. If I ask you to measure the instantaneous velocity, what you will do is you will measure the average velocity over the smallest possible interval containing the instant. Here we have a position time graph, and it starts off nicely behaved. Again, if we're talking about velocity, we want to look at the slope, and here the slope is constant and positive. But here in the curved portion, the slope, which again we mean the slope of the tangent to the curve, but the tangents to the curve have changing slopes. And what that means is that over the course of time here, you have changing velocities. Okay, please do this task. I want you to take this position time graph and show me the corresponding velocity time graph that you would get here. Please stop the show. I'm going to do it. Now you started the show again, and I hope that this is what you got, that in the first part there was constant positive slope, and so I would want to have constant positive velocity. I don't know what value because I don't have any numbers here. And then here there's constant 0 slope, and so I'm going to have constant 0 velocity over that corresponding time. Do not look at the fact that the positions are getting bigger and bigger, or the position is staying equal to some value. I only care about the slope, and that will guide you as you do this. Now go ahead and do these two. This is an issue about how you draw tangents. You might say that a tangent is a line that touches a curve at one point. Well, A does, but I hope you agree that that is not a good choice for tangent. I want it to touch at one point and capture the shape of the curve at that point. F touches at 2 points. Does that disqualify it from being a tangent? No, I mean locally tangent. Does F touch at one point? Yes, right here locally. Does it capture the shape of the curve? No, I think F's a bad choice. Who is the tangent here? Now what I would like you to do is take that same graph we dealt with before, but as it says on your worksheet, I would like you to find the average velocity over the interval from 0 to 3, and I would like you to find the instantaneous velocity at 3. Please show your work, make sure that your answer has the correct sig figs and units. I repeat what I have said before because it is so important to me. Instantaneous velocity is real. Things do have velocity at every instant, but you cannot measure it. All measurements will always be average velocities. If you're asked to find the instantaneous velocity, you will find the fill in the blank over the smallest possible interval containing fill in the blank. Thank you.